Hello, and welcome to the Advanced Response Engineering Online e-learning course video tour. What will follow are brief video segments from several training sessions to provide a glimpse of the training material for the Certified Quality Engineer training course. There is approximately 45 minutes of material available, so you may want to fast forward through some of the CQE course tour. When you are ready to register, please first view the free course registration and operation tour.
Welcome to the Certified Quality Engineer course, which is here to prepare you to take the ASQ CQE exam, or to provide you with an overview of the body of knowledge so you can apply it at the workplace and be prepared in the future to take the exam. It's a self-paced webinar offered in modules covering the various topics and subtopics that you can choose from as needed. Slides from these modules can be printed for your use during the exams. The instructors have been teaching these topics for many years within our ASQ sections and also as in-house training for multiple companies. Instructors have many years of experience in applying these concepts and methodologies at multiple employers in a variety of industries. And the instructors have actual hands-on experience working full-time in various companies and teaching these on a part-time basis. So the advantage of going through this course is that your instructors are working professionals like yourself. So quality philosophers and their leadership principles. Ones that we'll be covering is Schuhart, Crosby, Duran, Deming, Feigenbaum, Ishikawa, Taguchi, and Bill Smith. So Schuhart, he came up with the plan, do, check, act cycle and control charts, statistical process control, as you can see on there. So you can identify for processes and control and identify any out of control conditions that's attributed to special cause. Some milestones. 1924, introduced control charts. And then along with Dodge and Romig, developed acceptance sampling plans. And he published the economic control of quality of manufactured products. And then 1940 to 43, Bell Labs developed most standard sampling plans for the U.S. Army, which was covered earlier on in some of the recommended books that you can download off the internet. So common themes of quality. Improvement's never ending. Got to have top management commitment, knowledge, and active participation. Management is responsible for articulating the company's philosophy and goals, measurable objectives, and a strategy for change. All employees need to participate. Common language and set of procedures is necessary. And you have to have a process that's established to determine the most critical problems or causes and find solutions. So that supports the law of focus. And then changes in your culture, roles, and responsibilities may be required to achieve this. And if that's the case, then it's going to take time, along with commitment and constancy of purpose. So continuous improvement tools and concepts, such as SPC, TQM, Six Sigma, and Lean, including the theory constraints, will be covered in greater detail in other topic sessions in this course.
In our next lesson, we will cover some basics on data collection and data analysis. Statistics is a powerful set of scientific methods used to extract meaningful information from numbers. Data are collected and analyzed to draw conclusions regarding population measured and counted parameters. A population is considered the whole universe of the variable. For example, a process that makes ball bearings where the diameter is an important performance metric, the theoretical population of ball-bearing diameters would include all ball-bearing diameters from every ball bearing made by that manufacturing process. Because data on an entire population rarely exists, a sample, which is basically a small subset of the population, is used to estimate the population parameters such as the mean and standard deviation. An estimate of a population parameter made from a sample is called a statistic. There are three general types of data: variable, attribute, and location data. Variable data is continuous and is measured. For example, what is the diameter of the catheter? What is the tensile strength of a rod? How long is the part? And then attribute data is discrete and is counted. Some examples are how many rejects per lot, how many defects per part, how many people bought coffee with their breakfast. Two general areas of statistics are descriptive statistics and inference statistics. Descriptive statistics are used to characterize a sample. Sample statistics include measures of central tendency, such as the sample mean, X bar, the mode, and the median. Measures of variability, such as the standard deviation, S, sample variance, S squared, and the range, and other characteristics such as the minimum and maximum of the data, and skewness and kurtosis are measures of the sample distribution. Inference statistics deals with the collection, analysis, and interpretation of numerical data using the theory of probability to draw inferences regarding population characteristics such as the mean and the standard deviation. Statistical inference can be classified into two areas. First, estimating population parameters plus confidence intervals falls into that category. And next, hypothesis testing of population parameters, where we make statistical inferences about a population parameter being equal to or greater than or less than a hypothesized parameter. And we're going to be talking a lot more about all of this shortly. Sample statistics versus population parameters. When we collect data, it is wise to plot the data and see what kind of frequency distribution we get for the data. And here we have three examples of symmetrical distributions. The first one is normal, and that's a bell-shaped curve. And you can see that it's unimodal, one mode, and that the mean, the median, and the mode are all at the center. Another example of the data may be a bimodal distribution, where we have two modes, and then the mean and the median are in the center. And then a uniform distribution, where we have no mode, and the mean and the median again are at the center. Non-symmetrical distributions down here, where the distribution is skewed to the left. That means the tail runs out to the left side. And you can see that the mean, the median, and the mode are all in different locations. The data over here would imply that the data is highly skewed to the right. And again, the mean, the mode, and the median are in different locations. And identifying the distribution for the data is important so we know which statistical formulas to use during analysis. Two sample distribution characteristics I like to look at are skewness and kurtosis. Another very important plot is the box and whisker plot. This is another development by John Tukey. And what we have here is a box of the data. This represents the inner quartile of the data that goes from the 25 percentile of the data to the 75 percentile of the data. So this box represents the inner 50% of the data. And then from this line here, the first quartile down represents the first 25% of the data.
Welcome to the CQE Refresher course. In this session, we're going to cover topic number 2, which is the quality system. And those 18 questions are spread across 6 subtopics, being the elements of the quality system, documentation of the quality system, quality standards and other guidelines, quality audits, cost of quality, quality training. So looking at the quality system activities, you have quality and marketing. Places to look at would be the implied and stated needs of the customer, actual field performance, and customer satisfaction. Those are just some examples. Quality and specification design. So you need to be able to translate the clearly defined customer needs into technical requirements. Basically, the what's into the how-tos. Manage the design process, hold design reviews to ensure customer needs are met. Quality and purchasing. You have to define the requirements, communicate them to your suppliers. You need to be qualified based on their ability to meet those requirements. And the performance is monitored and communicated with the supplier. And you have your quality of process. All right, now we're moving on to quality audits, next major subtopic. So here in the body of knowledge, you got types of audits. So we want to be able to describe and distinguish between various types of audits, such as product, process, and management, also known as system audits. Achieve registration, such as certification, compliance, or regulatory requirements, and then first, second, and third parties. Level cognitions apply. Then number 2, roles and responsibilities in audits. So you got to define those roles and responsibilities for all the participants. Okay, such as the audit team, the client, and the auditee. And level cognition on that is understand. So, all right, some parties involved in the audit. These are legal terms. You have the client, the one requesting the audit. You have the auditor, so the individual is actually conducting the audit. And you have the auditee, it's the one being audited. So look at types of quality audits now. So you have internal quality audit. And internal is where the auditor is an employee of the organization. So they're on the payroll. It's also called first party audit. And that is a legal term. So all your internal quality audits are first party audits. Now external audits is basically where the auditor is an employee of the client or an independent organization, but not of the auditee. You got 2 types. You have the second party audit. So that could be yourself going out auditing a supplier. You know the supplier's payroll, and so you're auditing them. Third party audit is independent organization. Could be like a regulatory authority or a registrar. And they're free from political constraints. So remember, external audits are always second party or third party. So types of audits, there's the quality system audit.
We are at the beginning of our discussion of many important statistical tools. Before we begin our discussion on confidence intervals, I would like to review some important statistical concepts. Statistics is a powerful set of scientific tools used to extract meaningful information from numbers. In many top-performing companies, professionals use statistics to make database decisions. These are decisions that have a 95% probability of being correct, which means there's a 1 in 20 chance of being wrong, and that's considered acceptable by most professionals. If you were to take those same odds to Las Vegas, you would walk away a very rich man in a short period of time. Many of the hypothesis testing methods we're going to discuss require that the data are normally distributed or approximately normally distributed. Let's take a look at some common approaches that statistical practitioners use to determine if the data are reasonably normal. One approach is to plot the data on a frequency plot, like a histogram, and see if the data have a bell-shaped curve. Again, that approach is a little subjective. Another approach is to perform distribution fitting tests, Shapiro-Wilk, the Anderson-Darling technique, or the goodness of fit tests are three commonly used tests to fit the data to a distribution, in this case, the normal distribution. Caveat, if the sample size is small, i.e. less than 30, these tests have low statistical power and may not detect a deviation from normality when one exists. When the sample size is small, one approach I like to use is the normal probability plot. And that's this plot here on the right. And I had 10 data points, and they fall close to this line going through the center of the data. As long as the data are within what we call the fat pencil test, where you take this plot and lay a theoretical fat pencil on this line through the data, and all of the data points are within the width of that fat pencil, here shown with these two red lines. So we would look at these 10 data points and presume the data comes from a normal distribution. These same 10 data points plotted in a histogram would look like this. When the sample size is small, less than 30, sometimes the histogram, it's a little hard to. Let's begin our discussion on confidence intervals for the mean when sigma, our process standard deviation, is known. Let's look at an example. The average of 16 samples is x bar equals 40 with population standard deviation sigma equals 4. What is the 95% confidence interval for the population mean mu? 95% confidence implies alpha equals 1 minus 0.95, which equals 0.05. In this equation here, we took alpha because it's two-tailed, and we divide it by 2, and we get 0.025, or 2.5% of the probabilities are going to fall into each tail. Next, we want to go to the z-table and understand what z-value corresponds to a 0.025. So, if I'm looking for a z-value that corresponds with 2.5% to the right of that z-value, then I can look at the body of the table here, and I can see that at 2.5%, which is proportion 0.0250, corresponds to a z-value of 1.96. So I would have to move over 1.96 standard deviations to the right of the mean, and then that area to the right of that would be 2.5%. Now, because this is a normal distribution, The probabilities that apply to the right side, and that's what this table is just the probabilities on the right side. Those same probabilities apply to the left side because this distribution is symmetrical about the mean. Next, let's plug our values for our variables into our equation for the confidence interval. We had a sample mean of 40. We said that from the z-table, a z value that corresponds to 0.025 is 1.96, and we multiply that times 4, our process standard deviation, divided by the square root of n, our sample size. And we do the same thing over here on the right. And we end up with a range where we say we're 95% confident that the true population mean or process mean falls between 38.04 and 41.96. Statistical tolerance intervals are process tolerances based on the true nature of the process. You might call it the voice of the process. These tolerances may not be compatible with the customer requirements, called the voice of the customer. When the process is stable and normal, the statistical tolerance interval is defined such that a proportion, 90%, 95%, 99% of the process will fall within the statistical tolerance interval. Sometimes the statistical tolerance interval is called the statistical tolerance limits. The equation for the statistical tolerance interval is mu plus minus z alpha divided by 2 times sigma. If alpha equals 0.05, then mu plus minus 1.96 sigma will contain 95% of the data, explained by normal distribution theory. When mu and sigma are unknown, then we need to estimate the statistical tolerance interval from a sample, and the equation becomes x bar plus minus z alpha divided by 2 times s. Using this equation also requires a confidence level for estimating mu and sigma.
All right, next topic. So verification and validation. So on the body of knowledge, they want you to be able to interpret the results of evaluations and tests used to verify and validate the design of products, processes, and services, such as your installation qualification, your operational qualification, and your process qualification. Level of cognition is evaluate, so that is a high level of cognition. So your verification plans should include the following factors: dimensional wear, material fatigue, process variation, variation of critical characteristics through the range of the tolerances, contamination, environmental aging, extreme environmental conditions, and these are all examples. Extreme customer usage. So ISO 9001 requires that design developments be in a form that enables verifications against inputs. And designs need to be approved before release. ISO TS 6949 requires additional design outputs to define the APQP and the production part approval process. But as mentioned earlier in the course, they're not going to test you to the 6949. Test questions is going to be based more on ISO 9001. So design and development output should meet your input requirements, provide adequate information for manufacturing service, reference product acceptance criteria, specify any characteristics essential for safe and proper use. So verification is confirmation by examination and evaluation of objective evidence that a specific design specification has been met. And validation is confirmation by examination and evaluation of objective evidence that a specific intention has been met. The difference between these two activities entails who does them and the nature of your acceptance criteria. So verification and validation usually consists of design qualification, the DQ, installation qualification, IQ, and operational qualification, OQ, and performance qualification, that's PQ. Now, design qualification may be performed by a vendor or by the user by confirming through review and testing the product meets the written acquisition specification. And if the relevant document or manuals of the product provided by vendors, then the latter three Qs need to be thoroughly performed by the users. So that's the process of the IQ, OQ, and PQ is a task of verification and validation. So let's go through the definition of those, because it is mentioned in the body of knowledge. So the installation qualification. Welcome to our CQE refresher course. In this presentation, we're going to cover the body of knowledge, topic number 4, product and process control, part 2, subtopic C, which is acceptance sampling, which is a large subtopic. So when you look at the function of inspection, regarding the measurement of product characteristics, you can do 100% or a sample inspection. And with those measurements, you're comparing it to a standard. And you're making a decision as to the acceptability of the product or lot, to either accept it or reject it. Now, if rejected, should result in actions to mitigate the risks and take corrective action to improve the quality of the product or underlying process that's producing those products or services. So the topics that would be covered are sampling concepts, sampling standards and plans, sample integrity. So in the body of knowledge for sampling concepts, what they want you to be able to do is to interpret the concepts of producer and consumer risk, related terms, including the operating characteristic curves, the acceptable quality limit, the lot tolerance percent defective, which is also known as the rejectable quality limit, the average outgoing quality, and average outgoing quality limit. And the level of cognition on that is analyze. All right, some definitions. The AQL is known as acceptable quality level. So it's the maximum percent defective that can be considered as satisfactory as a process average. So what's really key to remember is that it's the maximum that you're willing to tolerate that's considered satisfactory as your process average. Now, if you exceed that, you get into the next one here, which is your lot tolerance percent defective, which is also known as the rejectable quality level. So it's the LTPD or RQL. So this is the largest percentage of defects that will make the lot definitely unacceptable. So your customers cannot tolerate more defectives than this percentage. So AQL is the maximum you'll tolerate, and your LTPD is that where you've crossed that threshold of pain and you're not going to tolerate it anymore and you're going to reject it. Okay, the next topic, sampling standards and plans. So in the body of knowledge, they want you to be able to identify, interpret, and apply ANSI, also known as ASQ Z1.4 and Z1.9 standards for attributes and variable sampling. And be able to identify and distinguish between single, double, multiple, sequential, and continuous sampling methods. Then identify the characteristics of diadramic sampling tables and when they should be used. Level of cognition is analyze. So variable versus attribute sampling plans, if you compare the two, variable sampling plans should be considered over attribute sampling plans when the measurement of a few parts is more efficient, such as less time and money, than the counting of many parts and the population approximates a normal distribution. So once again, you want to use variable if it's more efficient, but on the condition that the population approximates a normal distribution. So an example would be, as you see these two below plants having similar curves, an attribute plan, sample size of 125, C is equal to 3, and a variable plan, N is equal to 19, and K is 1.908. As you can see there, the sample size of a variable plan is a lot less. It's 19, where for the attribute plan, it happens to be 125. So in attribute sampling, to determine a sampling plan, you need to know the lot size, your AQL.
In this session, we will continue discussing hypothesis testing and working through several different examples. Let's begin our discussion with one sample hypothesis test for the mean. I have a table here of alternative and null hypotheses for the z-test and t-test. When our alternative hypothesis is mu greater than mu naught, this implies a right-tail test. And our null hypothesis, which is a mutually exclusive statement from the alternative hypothesis, would be mu less than or equal to mu naught. When we have mu less than mu naught, this implies a left-tail test. And our null hypothesis is mu greater than or equal to mu naught. And when we have mu not equal to mu naught, this implies a two-tailed test, and our null hypothesis will be mu equals mu naught. Where mu is the mean of the population of the sample, and mu naught is called the hypothesized mean, which can be a population mean or some target. In our first example, we'll do a one-sample means test with sigma known. A truck tire manufacturer claims their new brand of tires will last on average 40,000 miles with a standard deviation equal to 1,900 miles. A large trucking company is getting 35,000 miles with their current brand of tires, which costs the same as the new brand of tires. The trucking company has decided to buy this new brand of tires provided the tire life is not less than 39,000 miles on average. Determine if the new brand of tires should be purchased for the whole fleet of trucks. Step 1. Establish the null and alternative hypotheses. The way I like to approach this is to do the alternative first. The alternative hypothesis is what we are trying to prove. And in this example, I'm going to try to prove that the tires actually get 39,000 miles or less on average. And if they do, if I can prove the alternative, I will not buy the tires. Because my alternative is mu less than mu naught, then my null hypothesis is going to be mu greater than or equal to mu naught. In step 2, select alpha and beta risk levels. The team decided to use 95% confidence level with 95% power. The confidence level equals 1 minus alpha, which implies alpha equals 1 minus the confidence level, which equals 0.05. The power equals 1 minus beta, which implies beta equals 1 minus power, which equals 1 minus 0.95, which equals 0.05 for beta. So in this example, both alpha and beta equal 0.05. In step 3, we calculate the sample size. Performing a one-sample left-tail means hypothesis test implies we use the following equation. This equation is from slide 130, and we just plug in the numbers for a z of alpha of 0.05 and z for beta of 0.05, and we get 1.645 from the z table. And this quantity is summed and squared, and it's multiplied times our standard deviation squared of 1,900 miles. And in the denominator, E squared, we have 39,000 miles minus 40 to give us the minimum difference we want to be able to detect. And this quantity is squared. And we end up with 39.08 tires needed. And we round up to 40. We always round up the sample size to the next whole number.
Welcome to our presentation on risk management. In risk management, there are 3 subtopics to cover. It's risk oversight, risk assessment, and risk control. And you can look at it as identification, what are the risks, assessment, what is the likelihood of the risk occurring and how severe the risk impact be, then control, what can we do to reduce the impact of the risk, and then monitoring. Has the situation changed and are there new risks emerging? So on risk oversight, the body of knowledge, it's got 3 parts. There's planning and oversight. So you have to understand identification, planning, prioritization, and oversight of risk. Level of cognition is understand. And then metrics, which is another term for performance measures. So to be able to identify and apply evaluation metrics, the apply level. And then mitigation planning. So apply and integrate risk mitigation plan. And evaluate, which means, choose wisely. So in oversight planning, risk management is an increasingly important business driver as stakeholders have become more concerned about risk. Risk can be a driver of strategic decisions, it may be a cause of uncertainty in the organization, or it may be embedded in the activities of the organization. So an enterprise-wide approach to risk management enables an organization to consider the potential impact of all types of risks on all process activities, stakeholders, products, and services. And implementing a comprehensive approach will result in an organization benefiting from what is often referred to as the upside of risk, which is also known as rewards. There are risk management standards that have been published, such as the ISO 31000 Risk Management Principles and Guidelines. And this guide draws together developments to provide a structured approach to implementing enterprise risk management, also known as ERM. So this presentation does use content from this publication, and it's available on the internet for free. There's also the EU 14971 Corporate Risk Management Program, which is shown here as an overview. So you have your risk management policy, followed with an integrated risk management process for all phases of the life of the product. And then you have to have a culture and risk communication, and you have to look at the risks, the hazards, and the causes, and to display it on a risk graph. And then you have your residual risk. So what do you do there? Well, you have implementation of your risk control measures, training of personnel, and verification of effectiveness and post-production monitoring. The FDA has issued an industry guidance document back in 2006 called Q9 Quality Risk Management, which is available on this website. So some risk management tools. So below is a partial listing of risk management tools, and most of them are covered detailed in other presentations. There's the standard operating procedures, flow charts, process mapping, check sheets, cause and effect diagrams, and so on. There's the fair modes effects analysis, which we'll be covering, along with the fault tree analysis, and the hazards analysis and critical control points, known as the HACCP, and the hazard operability analysis, and the preliminary hazard analysis, risk ranking and filtering, and some supporting statistical tools. So we'll be covering some of these, starting here with the FTA, FMEA, and control plans. So contrasting between an FMEA and an FTA is your FMEA is a bottoms-up approach, considers failure modes at the lowest level, and determines effects at the highest level. Whereas with the fault tree analysis is a top-down approach, considers failure modes at the highest level and works down to determine causes at the lowest level. And for the type you use for an FMEA, it's used if there are multiple effects at the system level, and top events cannot be explicitly defined, and the identification of all failure modes is not important. Whereas for an FTA, the types of use, it's used if there's one extremely critical top-level event and the product functionality is highly complex and the product is not repairable once initiated. So let's cover an FTA, fault tree analysis.
Let's do a short review of previously discussed statistical tools. We discussed confidence intervals for the mean using the t-test and z-test, and we discussed confidence intervals for the standard deviation and variance using the chi-square test. Because we are estimating the process mean or standard deviation from a sample, there is a degree of uncertainty. It is necessary to place confidence intervals around our estimate for the true process mean or standard deviation. Next, we discussed tolerance intervals, and this is a technique where we let the process tell us what the specification limits are, or at least a technique that tells us what the process is capable of doing. Tolerance intervals give us a region where we can expect 95 or 99% of our process output to fall within that region with, say, a 95 or 99% confidence level. A lot of companies will also calculate the tolerance intervals when they're doing process validation activity, and if the tolerance intervals fall within the upper and lower spec limits, then they deem the process capable. Then we discussed hypothesis testing, and the first category of hypothesis testing we discussed were parametric tests, where we did 1 and 2 sample means tests using the T and Z distributions. Then we did process standard deviation and variance tests for 1 and 2 samples using the chi-square and F-test respectively. Regarding the process mean, we also discussed a hypothesis test for when we have 3 or more means to compare, and in that case we used ANOVA, analysis of variance, and again we used the F-test for that comparison. For the students taking the Six Sigma Black Belt refresher course, we also discussed non-parametric tests, and these are tests we use when the data don't come from a normal distribution. That is an assumption for the parametric tests to be valid, is that the data do come from a normal distribution. And when the data don't come from a normal distribution, we have alternative hypothesis tests called non-parametric tests. And in that case, we use the process median instead of the process mean that we used in the parametric tests. And we have alternatives for the 1 sample means test. It's a 1 sample median test called a 1 sample sign test. We also have an alternative for the 2 sample Z test or T test in the non-parametric tests called a Mann-Whitney test, which is an equivalent test. And for our process standard deviation or variance, we also have alternative tests. For the 1 sample standard deviation, we can use Bonet's test, and for the 2 sample variance or standard deviation test, we can use Levine's test. Preferred is the parametric test because the next topic we're going to discuss is my favorite statistical tool. It is design of experiments, and it is the most powerful statistical tool. It utilizes both hypothesis testing and regression analysis. The goal of the DOE is to generate a mathematical model that will explain how our system works. And then we will use this model to characterize and optimize our product and process performance. So let's begin our discussion talking about knowledge and DOEs. Design of experiments is the scientific approach used by researchers to effectively and efficiently obtain the knowledge necessary for breakthrough product and process performance.